Welcome to the Maths class, students. I'm Sowmya, your new Maths lecturer, who will be teaching for second PU students probability. Probability is one of the topic what you already had in your first PU syllabus. In the first PU syllabus, we had started defining probability. We had worked out few problems and properties on that. Now we continue in the second year with this topic probability and learn few more concepts. So whatever we have learned last year, we will revise that with few definitions and then come back to the concepts of second PUC. Now, the first thing what we learned last year in probability is random experiment. What is this random experiment? The definition says an experiment whose outcome cannot be predicted or determined with certainty in advance is called a random experiment. I'll just repeat, an experiment whose outcome cannot be predicted or determined with certainty in advance is called as a random experiment. Okay, what do I mean by this? Now here, whenever we cannot predict what will be the outcome, or we don't know what is the certainty of only getting that chance, such is called as a random experiment. Let me give you an example. A coin is tossed. Whenever I take a coin and toss it, I may get back head or tail. The chances of getting head or tail whenever I throw a coin. Now, I cannot predict what I will be getting, either head or tail. So, such an experiment whose outcome cannot be predicted in advance, that is with perfection, that I cannot say that it is head only or tail only, then such is called as a random experiment. If you consider one more example, a die. While playing any of the games, snake and ladder, all this, you use a die. It has 6 faces. On each face, there is number 1 to 6. So when you throw a die, you get back out of 1 to 6 any of one of these. So the chances of getting any one of this outcome with certainty you cannot predict. And that you will be getting this number only. Such is called as a random experiment. This is one thing what we have already learned. So a random experiment, when I define an experiment whose outcome cannot be predicted, that we cannot say what is the outcome, whether it is going to be head or tail when I throw a coin, or determined with certainty in advance. Before only I cannot predict what I will be getting. And when I throw a coin, I get tail only, I cannot say. Or I get an head only, I cannot predict in advance. That is called as a random experiment. The next one, what we learned last year in probability is sample space. Sample space is the set of all possible outcomes of an experiment. Just now I told you a random experiment can be a coin is tossed or 2 coins are tossed, a die is thrown. Now the set of all possible outcomes what we get back in that experiment is denoted as sample space. We call sample space as a set of all possible outcomes of an experiment. I denote sample space always by capital S. Now if I take a coin is tossed, then the possibilities what I can get back is head or tail. The sample space includes 2 conditions. One is head or tail. Whenever a coin is tossed, one coin when I toss, I get back chances as head or tail. These are the 2 possible outcomes. That complete set is denoted as sample space. One more I consider. A die is thrown. When I consider a die, the sample space of that is given as 1, 2, 3, 4, 5, 6. A die has 6 faces. From 1 to 6, any of this I can get back. So these are the 6 possibilities of getting back. So S denotes the sample space. It consists of set of all possible outcomes. When a die is thrown, these are the possible outcomes what I get. Now let me take when 2 coins are thrown. When 2 coins are tossed, 2 coins when they are tossed, what are the possible set of samples? I can get back leprosy. Now here, whenever I have two coins are tossed, I can get back the chances of on both the coins I can get back head. The first coin and second coin, both I can have head. The next chance is first one head and second one tail. The other one is first tail. In the first coin it can be tail and the second coin it can be head. What is the last possibility I can have? Both the coins can show me tail. So these are the possibilities, or this is the possible outcomes when two coins are tossed. On both the coins, the chances of appearing head is possible. Or on both the coins, chances of possibility of tail. Or in one head, first one head, second one tail. First one tail, second one head. So these are the four possible outcomes of an experiment when two coins are tossed. So each point is called as a sample point. Sample space is the set of all possible outcomes of an experiment. These are the possible outcomes when a single coin is tossed, a die is thrown, two coins are tossed. You denote a sample space by S. The next one, event. An event is a subset of a sample space. Just now we learned how to write a sample space. Whenever an experiment is done, the sample space is denoted by capital S. And I gave you a few examples, which are the experiments what we do, like coin, or it is a die, or two coins. Now, what is an event? An event is a subset of the sample space. Now, let me take the example, two coins are tossed. The first thing we learned was how to write sample space. In the last one also I considered this example. Two coins are tossed. The sample space consists of four sample points. Four are the conditions what you get back. What are those conditions? When two coins are thrown, on both the coins I can get back head. On both the coins it can show tail. Both the coins can appear head or both the coins tail. Or the possibilities are one head and one tail. How is it? On the first coin head and the second coin tail. The next possibility is on the first coin tail, the second coin head. So these are the four sample points what I get back. The set of all this possible outcome of an experiment when two coins are tossed is denoted by the sample space. Then what is this event? An event is a subset of the sample space. Now when I say an event is a subset of the sample space, under this experiment when two coins are tossed, we wrote down the sample space. But I will give you a condition that the number of tails is exactly 2. What are the chances of getting only this? That is, number of tails is exactly 2. We have to get back on both the coins tails only. Then what are those chances? That is an event. That is denoted by E. This is the first one what I consider. Number of tails is exactly 2. First condition I consider. I denote this event as E1. E1 is a subset of the sample space. What are the conditions when two number of tails is exactly 2? The only condition is E. On both the coins, I should get back T and T. That is, the first coin also shows tail and the second coin also shows the tail. Now, even when I take, it consists of TT. This belongs to the sample space. So I can say E1 is a subset of the sample space. So based on this experiment, what are the conditions we consider? Based on that, what we write is an event. An event is a subset of the sample space. Let us consider one more example in this case. The experiment what I took was 2 coins were tossed. I have written down the sample space. Number of heads is at most 1. I get back the heads, at least one of the heads. Then, to write down the event of this, I will denote it as E2. Let E2 be the event. What are the possibilities I get back when the number of heads should be at most 1? Out of that, at least one should be head. The chances both cannot be head, I cannot consider this. At most 1, yes, the first one, HT, Then TH, maybe on the first coin will show head or on the second coin. Even I can consider T comma T. At most, here, one head I should get. Otherwise also it is okay. If I don't get it, so T comma T. Sorry, TT also can be. So this is the event 2 under this experiment. Event is a subset of the sample space. Yes, these three are belonging to the S. So I can say E2 is also a subset of S. So we define what is a random experiment, where an experiment cannot be predicted in advance about the certainty. Sample space is the set of all possible outcomes of an experiment. Event is a subset of the sample space. With this, we also learned last year what is probability. Let us define probability and then start with second year solution. The next definition, probability. We define this in the first one. Probability of A is given as P of A is equal to number of favorable outcomes divided by total number of outcomes. Based on the event what we have, we write down the number of favorable outcomes. Total number of outcomes is given by the sample space. So probability is defined as number of favorable outcomes divided by total number of outcomes. Number of favorable outcomes are denoted by the event. What is the possible event they are given? Based on that, we will write down what is that favorable outcome. Then total number of outcomes is denoted by the sample space. Let me consider an example. 3 coins are tossed. When 3 coins are tossed, let me see what are the possibilities I get back. I denote the sample space is. What are the possibilities? Let me take down. On the 3 coins, when I consider, the 3 coins are thrown, all the 3 can show me head. On all the 3 coins, I can get back head. The next chance. The first 2 coins can show head and the third one can show tail. The next possibility is first and the third one will show head. The middle one shows tail. The next chance is the last 2 can show head, that is the second and the third one, and first one tail. All the 3 can get back head. 3 coins, all the 3 can show head. Otherwise, 2 coins will show head. What are those possibilities? First 2, first and the third one, second and the third. Whereas the remaining one will be the tail. Then the next chance is which tails I consider. Now the first 2 or the first and the third one will show tail, the middle one head. Then the next chance is first 2 will show tail and the last one head. First one head, the last 2 tail. And the one more possibility what I have left out is all the 3 coins can show. So these are the possible outcomes of an experiment when 3 coins are tossed. When 3 coins are tossed, the possible outcomes what I can get back. All the 3 can show head or all the 3 can show. Or 2 of them can show head and 1 tail. Those are the 3 conditions. Or 2 tails and 1 head. With first 2 tails, the third one head. Or first one head, the second and third tail. First and the third one tail and the middle one head. Or the possible is last one, all the 3 tail. Totally, there are 8 possible outcomes what I have. So the number of possible outcomes, what I have, the number of total outcomes in the sample space is 8. Now for this, let me consider an event. What is an event I can consider? I will take an example where event E1, I consider all the 3 show head. I consider let all the 3 coins show head. Then what is the possibility I get back? All the 3. So the chances is only this. On all the 3, we get back heads. When all the 3 coins show head, this is the only possible what I get back in the event E1. Now, how many favorable outcomes in this? It is only 1. So probability when a 3 coins is tossed and we get back of all the 3 coins head, it is given by 1 by 8. 1 by 8 because all the 3 coins showing head is only one chance, one favorable outcome. And total number of outcomes in this sample space is but 8. If you consider another example like exactly one head appears, exactly one head if it has to appear, what are the 3 possible cases I can take? Only these 3. Exactly one head appears. Event E2 I take. Exactly one head appears. When I take exactly one head appears, what are the chances I can get back? I can get back THT, where only one head I have, HTT, and last case is TTH. These are the only possible. In this case, it is the number of favorable outcomes is 3. But total outcomes of this experiment remains the same, 8. So in this case, it is 3 by 1. Whereas in this case, it is 1 by 2. But in this case, when I take the probability, it is nothing but 3 by 8. This is what we learned about probability. One example I considered, we have worked out many problems last year with this. Using the cards, playing cards, die, and the coin. Now this year, we will start with the first concept in second PU syllabus, conditional probability. The first concept what we have in second PU syllabus is conditional probability. Now let me define what is conditional probability. We learned about probability, that is number of favorable outcomes divided by total number of outcomes. Now let us define what is conditional probability. If E and F, two different events, I denote one as E and the other one as F. If E and F are two events associated with the same sample space. Now, last problem what I considered was when 3 coins were tossed, I took 2 conditions. One was all the 3 showing heads and the other one was at least one head appears. Those are the 2 different events of the same sample space. Sample space I considered for 3 coins tossed, and in the same problem I considered 2 conditions. In one, the event E1 I took it as 3 heads appear. The event E2 I considered one head at least one. Similarly, like that it is defined. In the same sample space of whatever condition I consider, E and F are the 2 events what are associated. E and F are 2 events associated with the same sample space of the random experiment. The experiment can be either a coin, die, or any of the playing cards, different conditions. Now we can consider many conditions under this. Random experiment, the conditional probability of the event E given that F has occurred. Now, we are going to define the conditional probability of the first event E given that the second event has appeared. The first event E given that F has occurred is denoted as probability within brackets event E such that the event F has occurred is given by probability of event E given that F is occurred is defined as probability of E intersection F divided by probability of F. Probability of E intersection F divided by probability. Provided probability of F is not equal to 0. We cannot get probability of F is equal to 0. Probability of F, the second event becomes 0. It is not defined at all. We cannot consider this. So the condition is in the denominator, I have to get back a solution. I cannot have it as 0. It is not equal to 0. That is condition for defining this. Now what do I mean by this? I consider for any of an experiment a sample space. From that sample space, I consider 2 events, E and F, which are occurring. Then the conditional probability is given by the conditional probability of one event E given that the F is intersection F. Two events are occurred. We will take out the common ones and write down the intersection of E intersection F. Probability of E intersection. What is the probability of E intersection F? Again, the number of favorable outcomes in E intersection F divided by the total outcome. Divided by, I'll consider only for the F event. What is the F event? The second event, what is appearing? Probability of F is number of favorable outcomes in the event F divided by total number of outcomes. So individually we find this. Then the conditional probability is given as event E such that F has already occurred is given by probability of E intersection F divided by probability of F. How do we solve this? Any experiment when it is given, we write down the sample space. The two events, what are the conditions given? We will find the event that is the subset from the sample space, E and F. Then the conditional probability to find, first we will obtain what is the intersection of the two events, E intersection F. Then find probability of E intersection F divided by probability of F. That gives conditional probability of event E given that F has occurred. So using this conditional probability, we will consider few of the problems. Before that, there are few properties what has to be. We will prove those properties and then come back to the problems. Before that, I'll just repeat the conditional probability. I'll just repeat once. Conditional probability. If E and F are two events associated with the same sample space of a random experiment, the conditional probability of event E given that F has occurred. Event E given that F has occurred. That is probability of. You denote it as E such that or given that F has occurred. You read it as probability of E given that F has occurred is given by, the definition is probability of E intersection F divided by probability of F. Provided probability of F is not equal to 0. Let me consider one example. Say you how to apply this formula, then we will prove with the properties. So this is the formula what you have to remember for conditional probability. The same thing can be reversed for probability of event F given that E is appearing. Probability of event F given that E is appearing or occurred already. It is given by probability of again E intersection. What are the two events? We take the intersection. Divided by which event was occurred. Here event F was occurred, so you divide by probability. Here event E is occurred, so it is probability of. The same thing can be interchanged. Either event E such that or given that F is occurred. Or here I will take event F given that E is. So this is how we arrange. Which is occurred, you divide by that. If F is the event occurred, you divide it by probability. If event E is occurred, you divide by probability of E. Let me take one example for this. I'll consider one example on conditional probability. They've given if probability of A, one of the event, is 7 by 13, probability of B 9 by 13, and probability of A intersection B is 4 by 13. Two events are occurred. What are those? A and B. They're given what are the probabilities of that. And A intersection B is found and the probability of that is obtained as 4 by 13. Evaluate. Whenever it is denoted by this, it is conditional probability. Probability of A given that B is occurred. Probability of the event A given that B is occurred. We know the definition, how to write down this. Probability of A given that B is occurred is a conditional probability. It is defined as probability of A intersection B. Probability of A intersection B divided by which event is occurred. It is probability of B. Probability of A intersection B divided by probability of B. What is probability of A intersection B? Already it is given in the data. It is 4 by 13 divided by probability of B was the event which was already occurred. What is the value of that given by? 9 by 13. So the denominators I can cancel 13 and 13. I get back 4 by 8. Probability of A given that B is occurred is nothing but 4 by 8. This is one of the example what I was. Similarly, we have few more. We'll work out those. Before that, we will start with some of the properties. So we will work out on conditional probability few more problems. This is one of the example what we have considered. Next one, properties of conditional probability. We define what is a conditional probability. Conditional probability of event E. Given that F is occurred is given by probability of E intersection F divided by which event was occurred F. So probability of F. Based on that, we will work out few properties. Let E and F, again two different events as E and F, be the events of the sample space F. There is an experiment conducted and S is the sample space of that experiment. E and F are the subsets. That is, whenever we say events, it is the subsets of the sample space. So there are two events what are considered under the sample space E and F. Then we have the first property is conditional probability. Probability of event S given that F is occurred is equal to 1. Similarly, probability of event F given that F is occurred is also equal to 1. So these are the two what we have to prove. Let me repeat this. Let E and F be the events of a sample space X, of a sample space S, of an experiment. Then we have first property, probability of event S given that F is occurred is equal to conditional probability of event F given that F is occurred is equal to 1. So two conditional probabilities we have to do. Let us try to do. Now we will start with the first one. The first one when I consider it is given conditional probability of event or sample space S given that F is occurred. Let me try to prove this. To prove this, I'm going to use the same definition. What is the definition we have? Probability of intersection of two what I have considered. What are those? Sample space S and event F. So S intersection of F divided by probability of which event is occurred F. So this is the definition of the conditional probability. What do I have? Conditional probability of S given that F is occurred. From the definition, I have probability of S intersection F divided by probability of F. This when I consider to prove it as 1. What is S intersection F? If I look at S, it is the sample space. It consists of all possible outcomes. What is F? It is an event of the sample space. Event means it is a subset. F is a subset of the sample space. We have studied last year in set theory on operations of set, intersection of set. Whenever universal set, intersection any set it is given. For a universal set, intersection A is nothing but A. Because universal set consists of all the elements and A consists of few elements. But when I take the intersection operation, it is only common elements what I consider. So similarly here, I have S intersection F. When I take S intersection F, S is the sample space which consists of all possible outcomes. And F is an event which is a subset of S. So I get back probability of F. Intersection of S and F will be F only, that is probability of F divided by probability. It gets cancelled, that is equal to 1. That is what is asked to. So you use the definition by the condition of F intersection F. I got back this as probability of F, which is same in the denominator. Cancel that and do it as 1. So this is the first condition. Similarly, let us do the second condition. The second condition to do that. Let E and F be the events of a sample space S of an experiment. Then we have conditional probability of event F given that event F is occurred. It should be proved as 1. Let us see how. Conditional probability of event F given that F is occurred. For this I use the definition. What is the definition for this? Probability of. What are the two events F and F? Take the intersection of that. Probability of F intersection divided by which event is occurred? Probability of F. So probability of F intersection F divided by probability. Now what is F intersection F? In set theory, you also studied that A intersection A is A itself. A only. Common elements, both the set are same. So same are the elements what we get at A. So probability of F intersection F is nothing but probability of F divided by probability of F, that is equal to 1. So these are the two conditions what we prove. Based on that, it proves the result that conditional probability of sample space S given that F is occurred is equal to 1. Conditional probability of event F given that event F only is occurred. Same event when I consider, it is nothing but it is equal to 1. So this is the first property what you have. Properties of conditional probability, the second one. Second property what I have on conditional probability. If A and B are any two events of a sample space S and F is an event of S such that probability of F not equal to 0, then probability of A union B conditional, that is given that F is occurred, is equal to conditional probability of A event F is occurred plus conditional probability of B event F is occurred minus conditional probability of A intersection B event F is occurred. Let us try to prove this. Now, to prove this, I am considering equations. Conditional probability of A union B given that F is occurred. What is the definition it says? I get back the definition as probability of A union B intersection F divided by which event is occurred? Probability of. They are given A and B are two events of the sample space S. Two events are defined for one sample space S. And F is also one more event of the same sample space. All the three are subsets. Such that probability of F is not equal to 0 because that we get back in the denominator. It is not equal to 0. That is, it is not a null set. We have evidence in that. Then we have to prove conditional probability of union A union B. Event F is occurred is equal to conditional probability of A given that F is occurred plus conditional probability of the second event B given that F is occurred minus probability of A intersection B given that F is occurred. You learned last year one of the properties. Probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. This is one of the properties what we have learned last year in probabilities. This is conditional probability property. Similarly, where event F is occurred, we are learning. Now let us try to prove this. To prove this, I am using the definition of conditional probability. What does the conditional probability definition say? Probability of A union B given that F is occurred is probability of A union B intersection F divided by which event is occurred F. Now using the condition what I have, for that I will rearrange this as probability of, can I write down union and intersection what I have? This is nothing but distributive law. I can use distributive law and write this as A intersection F union B intersection F. A union B intersection F can be taken as A intersection F, A intersection F, first given A intersection F union B intersection F. I am using distributive law divided by probability of. I have used the definition of conditional probability, then the distributive law. Now for this, again I will use now the definition of probability of A union B. I have union of two. I consider that. So what do I get back? Probability of A intersection F, the first one, plus probability of B intersection F minus probability of A intersection F intersection with B intersection F. What is the property we studied last year? I am using that. A union B when I know probability of the first one plus second one minus intersection of. So probability of first one is what? A intersection plus probability of B intersection minus probability of intersection of this. All divided by probability of. All divided by probability of. Now I do this again. We continue here. I just wrote statement of the probability. Now if I continue this again here, I have probability of A intersection F plus probability of B intersection F minus I have A intersection F intersection with B intersection. I use distributive law. Again I reverse that. Can I write this as A intersection B intersection F? The operation uses intersection clause. So A intersection B intersection F divided by probability of F in the denominator. If I have some more difference of the term in the numerator, I can split that. If I have A plus B plus C divided by 5, I can write A by 5 plus B by 5 plus C by 5. Some more difference of the term in the numerator and a single term in the denominator, I can split it. I can write this as probability of A intersection F divided by probability of F plus probability of B intersection F divided by probability of F minus probability of A intersection B intersection F divided by probability of F. All the three gets divided. First one divided by probability of F, second one and third. What is this? Is it not a conditional probability definition? Can I say it is a conditional probability? A conditional probability. Conditional probability of A given that F is up. What is the definition? Probability of A intersection F divided by probability. Plus, again the definition if I use conditional probability of B given that F is up. Probability of B intersection F divided by probability. Minus probability of, what is here? A intersection B given that F is up. So this proves the result what I wanted. I wanted to prove probability of A union B, conditional probability of A union B given that F is occurred. Conditional probability of A union B given that F is occurred as conditional probability of A given that F is occurred plus conditional probability of B given that F is occurred minus conditional probability of A intersection F given that F is occurred. This proves the result. So I just repeat what we had on LHS was to prove probability of A union B. Conditional probability of A union B given that F is occurred. I use the definition. What is the definition? A union B intersection F divided by which event was occurred? I'll apply distributive law for this. A intersection F union of B intersection F. Last year we studied in probabilities. If it is probability of A union B, it is probability of A plus probability of B minus probability of A intersection B. So I use probability of the first one, A intersection F plus probability of B intersection F minus probability of the two what I have intersection divided by probability of F. I'll retain these two as it is. For this, again, I'll apply the property since intersection is the same operation. I take it as A intersection B intersection whole divided by probability of F. Split the terms. When I split, I'm getting back each as the definition of conditional probability. Probability of A intersection F divided by probability. This is the definition of conditional probability of A given that F is occurred. The second one, conditional probability of B given that F is occurred. Minus conditional probability of which one? A intersection B given that F is occurred. So this is the definitions for conditional probability, which proves the result. Conditional probability of A union B under an event F is occurred is given as probability, conditional probability of the first event A given that F is occurred plus conditional probability of the second event B given that F is occurred minus conditional probability of A intersection B given that F is occurred. So this proves the second property what we have. We'll continue from this in the next class. Again, there is one more property what has to be proved. We have proved with two properties. One more property will continue in the next class.